try and explain you how a PLL works as an FM demodulator. Okay, so how an incoming signal which has, let's say, frequency excursions around FC, that is the unmodulated carrier, how you can extract the message signal back. I mean, so most of you guys would have known how an FM signal is. You see, let's say this is an unmodulated carrier. Okay, it's a high frequency carrier signal having a single tone which is not modulated in frequency, phase, or angle. So let's say you have a low frequency single tone message signal which is supposed to modulate the carrier signal, and let's call these signals CT, which is my carrier. Okay, it's you can see the CT is a high frequency signal as compared to your low frequency message signal. Okay, so both are, to make the matters simplified, much simplified, both are single tone signals. Okay, whereas the message signal FM has a frequency smaller than FC. In most cases, it is much smaller than the carrier frequency FC. Okay. So what happens is that in a typical FM signal, you have the frequency, instantaneous frequency, which is being varied with respect to the amplitude of the message signal. So, for example, when you have this, the message signal has more amplitude, has more energy, the frequencies are more bunched together. They appear as more close to each other. So it is a high frequency content over here. And then in this region in time domain, it is much relaxed. Okay, where the message signal has a low amplitude, and then when there is a high amplitude again, you have more bunching of frequencies, more bunching of waves together. So it's like a high frequency over here. So the instantaneous frequency, as a matter of fact, the instantaneous frequency is being varied with respect to the message signal. Okay, without affecting the amplitude. So you can see where the amplitude is high, you have more frequency, you have higher frequency. So what this depiction, this graphic shows is that the instantaneous FM frequency, if you have, let's call this pi is my instantaneous frequency, well, around my carrier frequency FC, there's no change in the amplitude. Note that there's no change in the amplitude of the FM signal. So the FC is being varied with respect to, so you can add an addition, and that is with respect to, which is being varied with respect to the message signal. And KF, you can say, is the, let's say, the sensitivity of the FM modulator. Okay, so it's just like a proportionality constant. So as the message signal M of t is higher in amplitude, there's more deviation from FC, right? If MT is lower, then FC is small. So if the amplitude is low, FC is small. So that is the basic understanding of an FM signal. Okay, that is how the frequency is being encoded, okay, by the message signal. So if you might have to write this in terms of the radiance frequency, you can multiply this with 2 pi. So this instantaneous frequency of FM is, let's call this omega c, and then you have plus 2 pi kf of mt, right? Now, one thing more to notice is that FM is an angle modulation scheme, okay, as opposed to amplitude modulation, because you see the frequency and the phase are very closely related. It's not like if you're changing one parameter, the other doesn't change. They're very closely related. For example, a typical FM signal, let's say my FM signal is of the form, okay, so let's write this as so let's say I have a typical FM signal ST, okay, and it is of the form A sine of phi of t, okay, where phi of FM is the phase of the FM wave, okay, or the FM signal. So this is the phase of the FM signal, okay. So in which contains the information, okay. It is not an unmodulated carrier now. It contains the information from the message signal, okay. Now how this phase is related to my FM frequency, instantaneous FM frequency, is that you understand that, okay, this will be omega FM t So I can write this as pi of fmt or pi of fm. The derivative of the phase d by dt is my FM frequency, right? Is my FM frequency. So or instantaneous frequency. So I can write this as just like this expression. Okay, so it can come down over here as nicely as omega c plus 2 pi kf, which is just a proportionality constant, so that you have the variation with respect to the message signal in the frequency, in the unmodulated carrier frequency. So the phase becomes, you can see that the phase becomes pi of fmt is, if you integrate both sides with respect to time, well, you have omega ct plus a phase variation term which contains the integration. It's like a scaled integrator, okay? So it's a scaled integration. The scalar is 2 pi kf, integration of the message signal, m of, let's say, a dummy variable tau, d tau, and then the limits can vary from 0 to the present time index time t, okay? Right. So this is my phase. So you can see the phase and the frequency are very closely related, and they're related by the differential. So it just implies that if you are going to vary one quantity, frequency, which is being varied with respect to the frequency of your incoming message signal, so it doesn't mean that the phase is not being varied. Well, phase is also very closely related to the frequency. So these modulation schemes are sometimes called as angle modulation schemes. Okay, so phase and FM are closely related, and they're known as angle modulation schemes. So, well, returning back to the topic, how an PLL can be used to demodulate such a signal. I mean, the job is to somehow try and extract from an incoming FM signal back the message signal MT is, well, you need to have a circuit that can track the frequency variations with respect to the message signal and can produce an output that is going to replicate the frequency of the message signal. Okay, so that will be the demodulator. Now, what to do is, well, let's start with the basic PLL diagram. PLL has, if you guys have studied this in basic electronics course, it has 3 components. Okay, the one is first and foremost is the phase detector, which is in a sense a multiplier. So let's say we have an incoming FM signal. Okay, so the incoming signal is my FM, and let's say this is S of t. Okay, S of t is my incoming FM signal, and then this signal is fed to a loop filter, which is in a sense a low pass filter. And what the low pass filter does is it eliminates the high frequencies, which results as a product of the feedback signal and the incoming FM signal. So let's call this feedback signal as R of t. Okay, I hope this R and S is not okay, they're differentiable. Anyways, so I have an incoming message signal, FM signal ST, which has information in its frequency variations with respect to the message signal, and that is encoded. I'm interested to extract that message signal. Then I have a feedback signal. That how this feedback signal is being generated is that in the feedback loop, I have what is called as a voltage control oscillator. Now, what this voltage control VCO oscillator does is that let's say at the output of low pass filter, I have a control signal VT, and the voltage control oscillator, in a sense, also generates a local FM. Let's say RT and ST are both FM signals. To be honest with you, because you see what VCO is doing is it takes the input VT, which is the control voltage, and produces an output whose frequency is proportional to the voltage, right? If VT is more, the output frequency is more. If VT is less, well, the output frequency. So in a sense, the output of VCO is being controlled by the input control voltage V of t, right? So I mean, what I can do is, okay, I already have an expression of ST. Okay, so let me put the expression of ST. So if you recall what we did before, we have the expression of ST. So I'm just going to plug this phase over in S of t. So let's write the expression for ST and RT, and then we can evaluate what is the error signal. And this error signal is in fact, and you should also know that this is a negative feedback loop. It's a feedback loop, but it's a negative feedback loop. Okay, so the expression for ST, which is my FM signal, is of the form some multiplier constant A, sine of, and if I have this phase, if I can put this correctly over here, this is omega CT. So let's plug this over here. This is omega CT, which is my omega C is the unmodulated carrier frequency, plus 2 pi kf, which is the FM modulator, let's say sensitivity. Okay, and then I have integration m tau d tau 0 to t. This is the integration limits, and that is it. Okay. And to make this expression a little bit more convenient, well, what we can do is to replace this by, let's call this phi 1 of t. Okay, phi 1 of t is again the phase, right, in radians. So, but it's instantaneous phase. Okay, so it's instantaneous FM phase. Okay, now for RT, which is the VC output. Well, again, the if you may appreciate. I can write this as B cosine of omega CT plus another phase. Let's call this phi 2t. Okay, and you will see that you'll notice that phi 2 again is a very close resemblance. The morphology is very similar to phi 1 because where phi 2 is defined in terms of the control signal V2 in the block diagram. So V2 is my control voltage signal to the VCO, right? So this is 2 pi kV, where kV now is a proportionality constant, multiplier constant. Okay, which ensures that the output frequency or the phase is being controlled by the voltage signal proportionally. So this is V tau, d tau. So in fact, first we have m tau, now we have v tau, okay, which is a control signal for VCO. So you see, what this means is you take the derivative of both sides, okay. If you take the derivative of both sides, then d by dt of phi 2 is going to produce 2 pi kV into v of t, right? And what is this? Well, that's the instantaneous frequency, right? Because this is going to be added to omega c. So the phase of the phase of VCO is nothing but, in fact, the derivative of the phase. So derivative of the phase is the instantaneous frequency of VCO. Okay, so let's write this as such. So omega VCO will be equal to omega c plus 2 pi kV of Vt. Okay, so now you should be able to appreciate that why I'm saying that RT is also a locally generated FM signal, just like ST, because RT has the control signal Vt that is controlling the output frequency of the oscillator. Okay, because the instantaneous frequency of the oscillator around omega c is being controlled by the control signal Vt, right? So the morphology is very similar. So ST and RT are in sense both FM signals. Okay, having different phases, of course. One is the control signal, the other is the message signal. Now again, how to recover the message signal? Well, let's see the working of this loop. But before that, you should be able to see two assumptions in RT. One is, what I've said is that if, let's say my control signal Vt is 0. If I don't have any control signal driving VCO, then what does this imply is that my VCO is running in a free frequency, is running in a free state, and in that case, when you see that Vt is 0, then the free running frequency of VCO is Fc, is an unmodulated carrier frequency. Okay, so Fc is my VCO. Okay, so this implies that the VCO frequency in a free running state is at the unmodulated carrier frequency. Okay, that's the first thing you should notice. Okay, if Vt is 0, then of course there's no difference between the unmodulated carrier and the incoming FM signal, which has no frequency deviations whatsoever with respect to the message signal. Okay, it's just an unmodulated carrier. Okay, fine. The other assumption over here is that my signal RT is pi by 2 radians out of phase, is pi by 2 radians out of phase with respect to the FM signal. Okay, well, why that is so? Because we have to use a trigonometric identity later on, and you will see the reason. You will see the phase locking will be around pi by 2. Okay, I'll explain later on. But you can see we have a sine over here, and then we have a cosine, because what's going to happen? So okay, this is out of phase with respect to your FM signal ST. Okay, so what's going to happen is that if you're going to multiply ST and RT over here to produce an error signal, you can see that from the trigonometric identity, when sines and cosines are multiplied, you'll have a high frequency term at 2 mega CT, which is going to be filtered out by the low pass filter, and then you will have a DC term. Okay, because the two frequencies are the same, and this becomes equal to omega 2 minus omega 1, and then you will have a sine. Okay, so what we are interested is to have a phase lock condition, which is to be achieved by PLL. So you can't have that if you cannot use a cosine. It will be a sine and a sine term, because sine will be in phase with sine. So if you multiply sine and cosine, you will have sine of A plus B and sine of A minus B, and that sine of A minus B will be in phase of sine. Okay, so you need to have a pi by 2 radian out of phase. You need to set VCO, okay, such that it is pi by 2 radians out of phase with respect to the incoming FM signal. Okay, all right, or with respect to, sorry, not with ST, but with respect to unmodulated carrier. Okay, unmodulated carrier signal. That's it. Okay, so let's go ahead and generate the error signal. Now, the error signal you can see in the above depiction is just the multiplication of the incoming ST and RT. So you just multiply those two signals, and what you have is a high frequency term. You have two components, a high frequency term and a DC term. So you can see that. Okay, let's write the expressions down over here. So this will be A into B, and one is sine, the other is cosine. So this is sine of again omega CT. This is coming from the FM signal, plus phi 1t. That is my incoming FM signal, and then I have another cosine term, which is due to the VCO output, and that is again omega CT, again whose frequency is being modulated by the control signal Vt, which is the feedback loop control signal Vt. So that is pi 2t. So if you multiply cosine with sine, you must recall that sine of A. Okay, let's use the trigonometric entity over here. Sine of A, cosine of B is equal to half sine of A plus B. Sorry, sine of A plus B into sorry, there is no multiplication, we will have an addition. So another term after another term plus sine of a minus b. Okay. So you can use this trigonometric identity to show that the resultant DC term out of the low pass filter is going to be a sine term. It is going to be in phase with the unmodulated carrier. That's what we are aiming for. Okay. All right. Now, okay. So all right, I've used the same letters A, B. I've noticed now. But anyways, so this is my A and this is the B, the angles. Okay. So what you can do is just referring to this identity, you can come up with the error signal which has two components. So let's put them down. So the first one will be, okay, the multiplier becomes AB by 2, and then you'll have sine of omega CT. Yeah. Okay, so first we have the sum. So this is 2 omega CT plus pi 1 of t plus pi 2 of t. So that is your that is the sum term, which is the high frequency component coming out of the multiplier, and the second term is a DC term. Okay, so this is, let's take this in the brackets, and then I have another term which is the difference. That is simply sine of pi 1 of t minus pi 2 t. Okay, so you see phi 1 and phi 2, the difference is the error signal, right? So this term is going to be is not going to appear out of the low pass filter, and what we're going to have VT, you can see in the above block diagram of the Pll. VT is the low pass version of error signal. So if I pass my error signal to this low pass filter, okay, so in its argument, if it takes the error signal, then what I'm left with is a DC signal, that is AB by 2 and multiplied by sine of phi ET, where phi E is the phase error. Okay, it's the phase error between the FM signal and the VCO signal. Okay, it's the phase error. So that's the story. Okay, this is my this is the control signal, which is going to control the frequency of the VCO in the feedback loop. So to understand how it locks, well, let me write this VT over here again, back again. So on the next slide, okay, VT is AB by 2 into sine of phi of ET. Okay. Now there are two conditions. If first of all, okay, you know that phi of ET is the difference between phi 1 and phi 2. Okay, this is your the error phase error. Now if phi of ET is 0, then you have what you have is that if phi of ET is 0, there is no phase error. This implies that PLL is locked. PLL is locked. There is no phase error, so that means the incoming phase and the phase output of or the frequency of VCO is tracking the incoming signal. Okay, so PLL is locked to the incoming signal. PLL is locked. There is no phase error. The other condition is, this is the first condition. The second condition is that if your phase error is small, if the phase error is small, could be less than 1 radian or so, if phase error is small, then we say that this implies that PLL is about to lock, is in near lock. So this implies PLL is about to lock. So the incoming frequency is in the capture range, so PLL is about to lock to the incoming signal, so it's about to lock. And in that case, in the second case, VT, when your phase error is small, it can be approximated as AB by 2, and you can forget about the angle, you can forget about the sine function. It will be phi of ET. Okay, why? Because if the angle is small, then you know that whatever the argument the sine function takes, if the angle is small, if x is small, then this is approximately equal to x. Okay, because the other term is going to include x cubed by 3 factorial. You don't need that. So it's a small angle. So you can well, provided that if x is small, then you can write it as sine of x is x. Okay, if x is small. So that's what we have done. Okay. If you want to expand this a little bit more and you want to recall what the error was, I can write this for you. So VD becomes now equal to, as an approximation, as AB by 2, and in near lock conditions, this is phi 1 minus phi 2. Okay, phi 1 t minus phi 2 t, and if you recall, phi 1 was my FM signal, and phi 2 is the phase of the VCO. Okay, and both has the multipliers, so I'll have 2 pi, I can take 2 pi out, then I have AB by 2, and then KF, KF is the multiplier constant, frequency sensitivity constant, you can say, of an FM modulator, and then KV was the frequency proportionality constant for VCO. Okay, and then I have to multiply this with an integration 0 to t m tau minus v tau d tau. Okay, so that's the difference. This is my I have this sort of a voltage control signal. Okay, if you still want to simplify this, what you have is pi AB into KF by KV. Well, you see, the idea of simplifying this and writing this in this form is to show you that this thing, AB by 2, is the open loop gain of your PLL. Okay, and if you have a very large open loop gain, well, that is required. If you have a very large open loop gain for all frequencies, then the large open loop gain is going to ensure that your PLL can track the incoming frequency excursions or frequency variations in the FM signal. That's important. So my open loop gain, okay, the loop gain of PLL, and you can see that there are many multipliers over here. And you see, if you expand this, you can absorb this even KF and KV over here. So to make the matter simple, I'll just write this as the open loop gain is my AB by 2. Okay. And some text it is more involved, and you can include the KF and KV proportionality constants as well. So there is a difference. Okay. And this difference is being multiplied by AB, which is again multiplied by pi. So you will see that this is much greater than, this will be much greater than 1 for all frequencies. And in that case, what happens is, if you have a open loop gain much greater than 1 for all frequencies, then for a typical feedback loop system, which we have over here, it's a negative feedback loop system, the transfer function of such feedback systems can be, if it is a linear feedback system, then it can be approximated by the inverse of the transfer function of the feedback path. What I mean is, if I have a large open loop gain, so let's say, okay, let's say we have a feedback system like this, a typical negative feedback system like this. I'm just creating for this as an example. and this is my feedback beta. The feedback path is, the gain of the feedback path is beta, feed forward path gain is alpha, and this is being fed back, so this is with negative, and this is my incoming signal, let's say VF in, and let's call this as VF out. Okay. Well, if you work out the transfer function from this block diagram, the transfer function works out to be quite nicely equal to V out by V in. In terms of alpha and beta, this is equal to A alpha over alpha beta plus 1. Okay. But the open loop gain, if alpha beta, if the open loop gain is much greater than 1, then as a consequence of the linear feedback theory, you can approximate this transfer function by the inverse of the feedback path, that is 1 over beta. So what does this mean? What implication of having a large open loop gain on tracking of the input signal of a PLL is that all you need to consider is now is in the feedback path you have the VCO, okay, and what kind of a transfer function the VCO has, so that we can take the inverse and we can reformulate or we can redraw the whole PLL block diagram in terms of the inverse transfer function of a VCO and see how it tracks the incoming signal then. So let me redraw let me redraw this block diagram. So what now we have is, okay, we'll have a difference of the incoming FM phase phi 1. It consists of the information from message signal, that is my phi 1 of t, and then I need the difference. Okay, phi 2 is the phase difference which is being generated by your VCO, and then this generates what is known as the error signal in the PLL block diagram, and this has to be multiplied by a scalar which is again your open loop gain AB by 2, and this goes into let's say, okay, let's to make things more simpler and to apply the linear system theory, linear feedback theory, assume that your filter has an impulse response HT, okay, and as far as electronics is concerned, let's assume that the filter consists of all linear components based on RC or op-amp if it is an active filter. It's a linear filter, right? And the impulse response is representing an LTI system. Okay, so what it does is ET convolutes with HT to produce a voltage controlled signal VT, and I can write this as such that, okay, V of t is equal to basically this is ET, so I'll have E tau HT minus tau, and I have convolution integral which generates my voltage control signal d tau, and then 0 to t. Okay, my error signal is the difference of the incoming FM phase and the VCO phase, and which is being scaled by the open loop gain AB by 2. Okay, and then it is convoluted with the impulse response of my filter, and then this VT signal is fed back to an integrator which is modeling my VCO, and this integrator is a scaled integrator, so it's 0 to t dt, and then the scaling is with respect to what is a scalar? If you recall, we have the frequency proportional 2 pi kV constant. Okay, so that's my scalar. Well, why do we have this? If you recall, what was my phi 2t? Okay, Let's write phi 2t, the expression of phi 2t that we discussed earlier on. This is my phi 2t. This is the phase of VCO, right? And this is my control signal, which is generating this VCO phase. So what I have over here is now, okay, let's, you see why I draw a scaled integrator in the feedback path is, to generate phi 2t, I need to scale my integration first of all with 2 pi kV, and then my VCO has to generate the instantaneous phase with respect to the control signal Vt. So this is V tau d tau 0 to t. Okay, that means the instantaneous frequency is being controlled by the controls by the control signal Vt. So this is my phi 2 of t. So I have to generate this, right? To compare this with the incoming the FM signal. Phi 1t is 2 pi. Okay, let me put this down for you as well. So we can keep track for phi 1t. Phi 1t is 2 pi kf, and that because it already contains the. I'm not drawing the FM modulator over here. I'm just drawing the PLL to demodulate the FM signal. But phi 1t already contains information from the master signal in its frequency variations with respect to the master signal MT. And you see this error signal which is generated. Where is the expression for error signal? Okay, over here you can see the error signal is just a multiplier AB by 2 multiplied by the difference of the phase. Okay, and if I've said that if this angle is small, okay, once passed through the low pass filter, this is AB by 2 into the difference of the phase. Okay, so but this happens after it passes through the low pass filter. So I need to multiply this with AB by 2 to generate the error signal. The error signal is in sense the difference of the two phases, and then it gets multiplied by AB by 2. It passes through the low pass filter, which I have said that is a linear time invariant system. So you can see that this entire block diagram is this entire negative feedback system is representing a linearized model of feedback PLL system. Okay, this is a linearized PLL system. Linearized PLL system, feedback PLL system. So you see over here again, if the condition is now turning back to the same feedback theory, if my open loop gain is much greater than 1 for all frequencies, if AB by 2 is much greater than 1 for all frequencies, for all incoming FM frequencies, instantaneous frequencies, then what I can do is I can replace the entire block diagram with the transfer function of the inverse of the feedback path. So a similar situation arises that I don't need to write the transfer function in terms of V out over V in, considering the feed forward and feedback gains alpha and beta. It's simply 1 over beta. So what do we have over here is how do we well, the question is, what is the inverse of the VCO? Okay, what is the inverse of VCO? So in time domain, it will be, if it is a scaled integrator, the time domain behavior will be another scaled differentiator. Okay, so what you will have is for incoming FM signal, if your open loop gain is much greater than 1, then for incoming FM signal phi 1t, it goes into a multiplier if the open loop gain is much greater than 1 for all frequencies, and we will have a reciprocal of 2 pi kV, so this becomes 1 over 2 pi kV instead, right? And then the time domain behavior of the VCO can be described as the inverse of the transfer function as the differential, so it becomes d by dt, and that's how you are generating the output. You note that we don't have any feedback right now. The entire system is being represented by the inverse of your VCO transfer function. So what we are writing over here is the closed loop time domain behavior. We are just showing the closed loop time domain behavior of PLL. Now it's being described by the overall output voltage Vt, produce in response to the incoming angle phi 1t by the incoming signal as the derivative of phi 1. Okay, so now the control signal, so there is no feedback. Okay, Vt is now, so the entire thing is, this is the inverse of the VCO transfer function. So Vt is my 1 over 2 pi kV into d by dt of phi 1t. And if you recall, what was the situation before? Well, VAT, the control signal, which was controlling the frequency output of the VCO, was due to the phase was phi 2, but now we have phi 1 over here, right? And what is phi 1? Phi 1 is due to the message signal, right? I mean, if you look at this expression, that means that the derivative of phi 2 with respect to time, and scaling this by 1 by 2 by kV generates Vt. But now you can see that this is being done by phi 1. So if you plug phi 1 over here, in near phase log conditions, if the open loop gain is much greater than 1, then PLL is going to in fact track your incoming FM frequencies so that the control signal becomes proportional to the message signal. So the idea is like this. Okay, so if you plug this over here in near phase log conditions, what is my phi 1? Okay, that is 2 pi kV, not kV, that is kf. 2 pi kf integration of 0 to t m tau d tau. So what I have over here is, now you see the 2 pi goes out. I just have a proportionality constant, again some new proportionality constant, is the ratio of kf by kV, and then this integration and differentiation is cancelled. So this is equal to mt. Well, what does this mean is that in near log conditions, I have Vt. Well, this thing implies that Vt is proportional to the message signal. If Vt is proportional to the message signal, then guess what? The VCO, your VCO over here in the PLL, is going to produce the output frequencies which are in accordance with the message signal, right? So if the message signal amplitude is high, the frequency is high. If the message signal amplitude is low, the output oscillator frequency is low. So it's just like tracking the FM signal, right? So we are tracking the instantaneous frequency of the FM signal with respect to MT, because MT is now proportional to VT, okay? Or VT is proportional to MT, right? When you have a near phase log loop. So that's how you are more demodulating the FM signal, right? So your VT, now once you have demodulated the FM signal with PLL, your VT should be proportional to MT. So the control signal is tracking the message signal. So that's how you get the message signal out. Well, there won't be any change in the spectrum. In fact, there will be just a multiplier, but no change in the spectrum. That multiplier is the ratio of KF and KV. That is the frequency sensitivity multiplier constants of the FM modulator and the local VCO, which is again an FM modulator. Okay. So I hope you would have appreciated how the PLL works in demodulating the FM signal, provided that the open loop gain is much greater than 1 for all frequencies. That was the assumption. Okay, and if that is the case, then based on the linear feedback theory, when you have a linear SPL model, because we say that okay, your filter is again linear, integration operation is a linear operation. So what you have is you have is a linear feedback PLL model, and if the open loop gain is greater than 1, then PLL is able to track the frequencies, and you can show that by taking the inverse of the VCO, okay, over here, which is nothing but the scaled integrator, and you can, the time gain behavior of how you can express this as an inverse of this transfer function of the feedback path is that it will be an inverse scalar, okay, 1 over 2 pi kV, and then differentiator, so no feedback. So VD is produced directly from phi 1, and if you plug the definition of phi 1, well, phi 1 is due to the massive signal. So that's how the control signal of the VCO begins tracking the massive signal which was once modulating your unmodulated carrier around omega c. Okay, so that's the idea, that this is how you get your massive signal demodulated from the PLL, provided that the open loop gain is much greater than 1 for all frequencies. Okay, well, that's all, and thanks for watching.